let's look at acceleration in this section. Some definitions. First, uniform motion. Uniform motion is a smooth acceleration. It's a constant acceleration. Non-uniform motion is when things are changing. So, what's the motion? He's not moving, is he? Maybe it's a girl. I think there's a ponytail. Maybe it's a guy. Here, notice it's a constant velocity. No acceleration. Again, if you use that dot idea from the other day with the bird in our problems, let's put the dot just at the neck. Notice the dots on this person are evenly spaced. So we know this stick figure is not accelerating. Doing the same thing with this illustration, notice that the stick figure is showing accelerated motion. And this one is decelerating, which is just a negative acceleration. Looking at a velocity time graph, when we have a constant acceleration, we're going to have a nice linear relationship. You will not have a curve where you have a changing acceleration. Our acceleration equation is your change in velocity, which is your rise, over your change in time, which is your run. So a new equation for you, average acceleration, is your change in velocity over your change in time. You can also look at that as your final velocity minus your initial velocity is divided by your final time minus your initial time. Most of the time, they'll give us a time period like 2 seconds. They won't specifically say like 10:30 and 10:35, so you have to figure out the time difference. Another term that I'd like to mention to you is instantaneous acceleration, and that's the change in velocity during an instant of time. If we can look at a graph and we draw a tangent to the curve, okay, the red line is the acceleration graph, where it touches would give us the instantaneous velocity. Here you can see it's a constant, I should have said acceleration. I believe I said the wrong word. So, when you have a curve, you have a changing acceleration, and when you have a nice straight line, it's going to be constant. Now here's that dot idea showing an acceleration, and one way to determine it, you can use 2's and 1's, you also see f's and i's. So your final velocity minus your initial velocity over the time period will give you your acceleration. You do need to be careful with direction. Something going to the right will be a positive direction. Any motion to the left would be a negative direction or a negative velocity as noted here. If we look at those two, we're adding these two vectors together, we see that difference right here, and that shows us our direction of the acceleration. So acceleration. When the velocity and acceleration vectors point in the same direction, the object's speed increases. When they're in the opposite direction, you're going to have a decreasing acceleration. Notice this one. Here's our decreasing acceleration. Dots are getting closer and closer. If we look at this, we have a decreasing acceleration. When the velocity vector and the acceleration vector point in opposite directions, the object slows down. So let's work some problems. That'll clarify things for you. So our first problem. Race car's velocity increases from 4 meters per second to 36 meters per second over a 4-second time interval. What is its average acceleration? In physics, you want to list your variables. So VI, its initial velocity, is 4 meters per second. 2 sig figs, huh? Its final velocity is 36 meters per second. The time interval, I usually just list t. You can list delta t, is 4 seconds. Remember our basic equation. I really want to see that on your paper. It's your delta v over delta t. We can also expand that. Final velocity minus initial velocity over delta t. Let's put in our numbers. 36 meters per second is your final velocity. Subtract 4 meters per second and divide all of that by 4 seconds. So you end up with 32 meters per second divided by 4 seconds, dropping some sig figs just for simplicity's sake. And 32 divided by 4, we're back to sig figs. We only have 2, so 8. Notice the units. We have meters per second per second. The units for acceleration are meters per second squared. Every second, this car is going 8 meters per second faster. Another problem. This time the race car slows from 36 meters per second to 15 meters per second in 3 seconds. What's its average acceleration? Oops, let's go back. All right. So this time, VI is 36 meters per second. VF is 15 meters per second. Time is 3 seconds. We want to know acceleration. So A is equal to VF minus VI over T. If you make yourself write these, you will have them memorized before you know it. So A is equal to 15 meters per second minus 36 meters per second all over 3 seconds. Do your math and you get a value of negative 7, 2 sig figs, meters per second squared. This negative acceleration tells you that it's slowing. Okay, but you can also say it's decelerating. Slowing down. Our third one. A bus is moving at 25 meters per second when the driver steps on the brakes and brings the bus to a stop. In 3 seconds, what is the average acceleration of the bus while braking? So the bus is originally at 25 meters per second. It's coming to a stop, so the final velocity is 0. This all happens in 3 seconds. Again, average velocity is your final velocity. Average acceleration is your final velocity minus your initial velocity over your time period. So you have 0 as your final, because you're coming to a stop, minus 25 meters per second, all divided by 3 seconds. Do your math. Look at sig figs. Looks like 2, 8.3 meters per second squared. And let me bring in that negative, because it is slowing down. It's decelerating. I have one more for you. golf ball starts with a speed of 2 meters per second and slows at a constant rate of 0.5 meters per second squared. What is the velocity after 2 seconds? Its initial velocity is 2 meters per second. It's slowing at a rate of 0.5 meters per second squared. So that's your acceleration. Make sure that you put the negative sign in there. We're trying to find its velocity, so we're trying to find its final velocity, that's our unknown, after a time interval of 2 seconds. Now, your basic equation is A equals VF minus VI over, just going to write T. In physics, you should rearrange your equation to isolate your variable before you plug in the numbers. So I'm going to do that in steps for this first example. I'm going to multiply both sides by T, and you'll have, there we go. Hopefully it comes back. There you go. We have AT equals VF minus VI. So I got that by multiplying both sides by T. So you have acceleration times time equals VF minus VI. We want VF by itself, so I'm going to add initial velocity to both sides. So now I'm going to have VI plus AT equals VF. That's the equation I want to work with. Usually we write it VF is equal to VI plus AT. I'm going to put a box around that. That's my working equation. Let's go ahead and insert our numbers now. Our final velocity is equal to our initial velocity, which 2 meters per second, plus negative 0.5 meters per second squared times 2 seconds. Do your math, which I know you're great at. You should end up with 1 meter per second as the final velocity. Think about if that number came out to be negative 1 meter per second. What would that mean? If you're not sure, be sure to ask me tomorrow in class. That's it for notes tonight.